So good afternoon, ladies and gentlemen. Thank you for joining us today for this webinar session on the interesting topic, neural network-based approximation algorithm for nonlinear partial differential equations with application to pricing. This event is brought to you by the NTU Institute of Advanced Studies, the graduate student clubs of the School of Physical and Mathematical Sciences, and the Electrical and Electronic Engineering. My name is Shivam, and I'll be your host for this webinar. Before we begin, there are some housekeeping rules for this webinar. All of your mics have been muted to prevent any accidental disturbance. If you would like to ask a question during the Q&A session, please use the raise hand feature at the bottom of your Zoom screen. When your name is called, please ask your question. Or you can also post your questions under the Q&A feature at the bottom of your Zoom screen. For the postgrad students who require the endorsement of the attendance, please scan the feedback form at the end of the session and indicate the need for endorsement. Today's webinar is being organized as a part of Discovery Science Seminars and Interviews Initiative. Let me introduce the speaker for today's webinar, Prof. Ariel Neufeld. Prof. Ariel received his doctorate in mathematics from ETH Zurich and Columbia University, following which he did a postdoc at ETH Zurich. His research interests include machine learning in finance and insurance, model uncertainty in financial markets, and stochastic optimal control. He is currently a Nanyang assistant professor in SPMS NTU. He has received many accolades and awards during his academic career. Recently, he won the Society for Industrial and Applied Mathematics Activity Group on Financial Mathematics and Engineering Early Career Prize. Without further ado, let's welcome Prof. Ariel. Prof. Ariel, please.
Thank you much for this nice introduction, and thank you very much all of you to attend this talk. It's really a great pleasure to have this opportunity to present part of my research here at this webinar. So first of all, I hope everyone can see my slides. Let me do it in, hope this is fine. So today what I'm going to talk is, as the title is saying, I will talk about neural network-based approximation algorithms for nonlinear PDEs with application to pricing. And this is work, this talk is based on joint work together with Christian Beck, Sebastian Becker, Patrick Heredito, and Arnulf Jensen from ETH Zurich and the University of Münster. So what I'm going to do today is I'm going to first introduce you the motivation of why actually we're interested to develop neural network-based approximation algorithm to solve nonlinear PDEs and how it is related to pricing of financial derivatives. We're going to present our particular algorithm, and we will show that it actually can help to solve very high dimensional financial derivatives to be priced. So let me start with the motivation of the problem. So first of all, let me introduce, for those who are not coming from finance, what is an example of a financial derivative. So think of it that you have, let's say, one stock from one particular company. And let's say today's value is 100. And the bank offers a contract which tells you the following. You look in 1 year, the value of the stock of this particular company. And let's say if it's above 120, you get the difference. And since if it's in 1 year, if the value is 130, you get the difference between 130 and 120, so you get 10. Or if it's above 100, if it's 140, you get the difference between 140 and 120, which is $20. However, if it's below 120, you don't get any money from the bank. So this is a contract which depends on one underlying stock. And you see the question is, of course, now what is the fair price to sell this kind of contract, this kind of financial derivative? Because as you see, first of all, it depends on time development, because it's something which depends on the stock price, not of today's value, but in the future, here in the example, 1 year. And second of all, the additional difficulty, of course, depends on randomness, because stock prices, of course, depend also on random events. So you cannot know exactly what the value is going to be in the future, let's say in 1 year. So this is an example of a very simple financial derivative, so-called European call option, depending only on one underlying asset. But in practice, of course, financial derivatives might depend not only on one underlying asset, but on several ones. Think of it, let's say, of a financial derivative, which depends on the whole index. So for example, S&P 500, which would depend on roughly 500 different assets. So you see, so this already makes the dimension of the financial derivative already very high dimensional. So now you may ask, how can you actually price such a financial derivative independent of, let's say, the size of it. And for that, you need a financial model. You need a model to be able to calculate the prices. And typically what models developed over time are typically models which depends on some kind of, let's say, Markovian models, let's say stochastic differential equations. And typically as a consequence, the prices of financial derivatives can actually be written or expressed using the solution of a particular partial differential equation, shortly PD. So the dimension of the corresponding partial differential equation, which is, to be a little bit technical, it's typically a parabolic partial differential equation, so which depends on time and on space. Time, the current the value at time t of the price, and x, the current value of the corresponding stocks. The dimension of the PD corresponds to the amount of the underlying assets which the financial derivatives are involved. So, okay, so typically we have this financial derivatives which depends on a large amount of financial assets. You have a corresponding PD which you want to solve because this expresses the prices, so you want to solve a high dimensional PD. So if you start, let's say 34 years ago with the first model, think of it as Black-Scholes model for those who have taken some courses in economic theory. In idealized markets where there are no friction, the corresponding PD, like the Black-Scholes PD, is a linear PD. So for linear PDs, there are very efficient algorithms to solve them, even for very high dimensions. So there is actually no need to develop more sophisticated methods to solve them, because for linear PDs, already the classical methods involving Monte Carlo methods are very efficient. However, what's turned out, of course, what we've seen also with the financial crisis, is that these very simple models at the beginning are not very realistic, and you should impose more sophisticated models, which include, for example, friction or some kind of model uncertainty. And as a consequence, from an analytic point of view, the corresponding partial differential equation is not anymore linear, but it becomes a nonlinear PD. And from a numerical point of view, this has a severe consequence, namely that the complexity of the algorithm grows now exponentially in the dimension because of the nonlinearity, and there are not anymore any kind of efficient algorithms which can solve those nonlinear PDs efficiently. So we are faced with this problem that we have typically financial derivatives which depend on a huge amount of underlying assets. The corresponding prices can be expressed via a PD, which is, however, nonlinear if we want to use a more sophisticated model which represents more realistically the financial market. But unfortunately, classical methods are not able to solve high-dimensional nonlinear PDs. So if I talk about classical methods like finite difference or finite elements, typically they were able to solve dimensions 7, 8 maybe. But if you think of, for example, the S&P 500, dimension 500, we're far away from being able to do so. So this gives us the need to develop algorithms which can actually solve high-dimensional nonlinear PDs, so that we are able to also price financial derivatives, which depends on a huge amount of underlying assets. So what recently was the idea is that it turns out machine learning, deep learning has proven to be very effective to solve, in general, high-dimensional problems, such as, for example, computer vision. Think of it as classification, or object recognition, or in language processing to, for example, speech recognition. And what is the idea? To catch up one, for example, dealing with neural networks, is use a neural network to somehow learn, for example, how it should classify or to recognize some speeches. So what it does, technically speaking, you train a neural network. I will talk about this in a little second. You train the neural network such that it does the right job, okay? I will talk a little bit more this precisely, but of course, so a naive idea would be, okay, let's use a neural network to solve the PD, which hopefully, since neural networks have shown in other fields to be very effective to solve high-dimensional problems, hopefully neural networks can actually also solve high-dimensional nonlinear PDs. So this is actually, it's on the one hand very naive idea, but we will see how to do it. But of course, we need to have some justification and some ideas how we are able actually to do so. So let me first, before I start, let me first introduce to you from a mathematical point of view what we mean by actually a neural network, and why actually neural networks have this kind of good property that they actually can solve problems in high-dimensional problems. So what is a neural network from a mathematical point of view? A neural network, let's say an M-layered neural network, it's just a composition of functions here from 0 to m. So it's m layers. The composition of first, you have an affine function composed with a activation function, which is non-affine. So here the affine function is just of this type. It's really just a classical affine function on finite dimensional spaces. And then you apply, you compose this with a nonlinear function, the so-called activation function. And typical ones which are used are either the ReLU function, which is the following, or the sigmoid function. So neural networks are nothing else than this kind of compositions of functions. And you see, if you want to specify a neural network, you need to specify the parameters on the affine functions. So if you just count the dimensions, you see that you need to specify the following amount of parameters. Don't worry too much about this formula, but the key point of it is you see that this sum is finite. So you see, you just need to specify the finite amount of parameters to specify a neural network. And when we talk about training a neural network, means we want to find optimal parameters. So we need to specify a finite amount of parameters. So this turns out to be a finite dimensional optimization problem. Okay, so now we're all on the same page what we actually mean by a neural network, by M-layered neural network. So let me present to you one of the fundamental principles why neural networks are capable to learn properties such as for speech recognition or, for example, classification. One of the key properties is what is referred as the universal approximation theorem. There are several forms, but let me present one, probably one of the first results, which tells you the following. If you start on a compact space, then the set of even one-layered neural networks is dense in the set of continuous functions from X to R, dense with respect to the uniform topology. Let me mention that, of course, different results with respect to different topologies. And also different activation function. This result was proven with respect to the sigmoid function. Let me, for the mathematician here in the talk, let me present just shortly the argument how you can prove this. You see, it's a very short argument. So how do you prove this? Assume by contradiction actually that the set of neural networks is not dense. So there exists a continuous function which does not lie in the closure of the set of neural networks. Then using Hahn-Banach theorem, there exists a continuous linear functional L which vanishes on the closure of the set of neural networks, but actually gives the value 1 if you apply this element f, this continuous function. Now you apply this representation, which actually tells you that this linear function L can be represented as the integral. So there exists a Radon measure for which the linear functional can be written as an integral. So by the property of the linear functional that it vanishes on the closure of the set of all neural networks, you're going to see that this vanishes because you apply neural networks. And by the assumption that it vanishes on the closure, this has to be all equals to 0. And now you use the property of the sigmoid function that is discriminatory. I don't want to go into details here, but as a conclusion, you can actually conclude that the measure mu is actually 0. But this actually implies that the functional originally was 0, which is a contradiction to what we have assumed, that the functional gives the value 1 if applied f. So we have found the contradiction. So we see actually that there cannot be a continuous function f, which is not in the closure of the neural network. In particular, this means that the set of neural network is dense. Okay, see, this is just a short argument I wanted to present because I think it's not bad that people have seen this short argument. But the key essential property which you should take from this is, okay, you have the neural network possess the universal approximation theorem, which means every continuous function can be approximated in some sense by a neural network. And which is why this gives rise to the possibility that a neural network can actually be trained to learn speech recognition or classification, because exactly training means you try to approximate a continuous function in the right way. Okay, so since we have this universal approximation property of neural network, the idea is, of course, to use neural networks to approximate the solution of the nonlinear PDE, because typically what you can show on the sum regularity assumption that the PDE, which the solution, let's call it Vt of x, depending on the time t and on the location x, t represents the time, x the position of your stocks. is typically continuous in those variables. So you have the universal approximation theorem, which tells you, yeah, actually your neural network can your solution of the PD can be approximated by a neural network. However, there's a catch with this theorem. The theorem is an abstract one in the sense like, okay, you have this density property of the set of neural networks, but of course nobody tells you actually how to find a good neural network which approximates your continuous function which you would like to learn. For example, the solution of the PDE. So how can we use the universal approximation property of the neural networks such that we can learn the solution of our nonlinear PDE? And so how can we learn the solution of PDE? So if you remember, for those who have already used neural networks from a practical point of view, using some kind, let's say TensorFlow, for example, or PyTorch, what typically you do is you train your neural network. So training actually means, from a mathematical point of view, you apply an optimization problem to find optimal parameters on your neural network. So what we want to do, since we want to solve our PDE and we want to find a neural network which actually can approximately solve our PDE, we want to formulate the solution of our PDE as a solution of a optimization problem, which then a neural network can solve or approximately solve. And since we know that the solution of this optimization problem is the PDE, then our neural network will do the job. So what is our task? We need to find an optimization problem for which the solution of this optimization problem is the solution of our PDE under consideration. So how can we do this? So first, before let me explain to you how you do this, let me recall a property which most of you have taken advanced class in probability theory, have already seen this. So this is, you're going to be maybe surprised that I'm going to recall this, but you will see this even though elementary, it's really an essential property which we will use in our algorithm. So what does this tell us? If you have a family of random variables parameterized by x, such that the map x goes to expectation of the random variable x is continuous, then actually, if you look at this minimization problem that you want to minimize the quadratic error over all continuous functions, then the solution of this quadratic minimization problem is actually the expectation. Okay, so the expectation is a solution of a quadratic minimization problem. And what you should think of those random variable x6, think of it as solution of a stochastic differential equation with starting point x. Think of it as, from an application point of view, think of it as the involvement of your stock prices, where x is the starting point, the value, the spot price of your financial derivative, okay? So what we have found is that the expectation is a solution of a minimization problem, actually from the quadratic minimization problem. So naively, what we will say is, okay, can we somehow write the solution of the PD as an expectation? Because if we can do it, we know the expectation is the solution of a concrete optimization problem. And since we have found an optimization problem, we can use neural networks to then actually try to train and solve this optimization problem. And once we have found a good neural network which does the job, since we know that theoretically the PDE is the solution of this optimization problem, the neural network will approximately be the solution of the PDE. So how can we do this? So thankfully, this is not something new. So it's this very deep connection between partial differential equation and stochastic differential equation in stochastic calculus, which is referred as the Feynman-Katz representation, which tells you the following. Assume you have any kind of time t and you have a position x in space, and you consider the following stochastic differential equation. So this is the stochastic differential equation at time s, where you start at time t and at the position x, and you evolve, you see, from t to time s with this drift and this volatility. So this is the noise, and this is somehow the trend, if you want to think of it. And then if you want to consider the corresponding linear parabolic PD, which is actually the generator from the ST, which is the following parabolic PD, you have here derivative in time, so that's why you have parabolic structure. This, the first order corresponds to the drift. This, the second order term, corresponds to the to the volatility, and this is the boundary condition. Okay, then the solution of this linear PD can actually be written as an expectation, namely the solution of this PD is just the expectation of the boundary condition phi at the terminal time t, big T, applied to the SDE when evaluated also at the terminal time t. So for those who are not coming from PD theory, why it is linear? Because you see it depends linearly in V, linearly in the gradient of V, in the derivative of V, and linearly in the Hessian, in the second derivative of V. Okay, so what we see is Feynman-Katz representation actually already gives us a way how can we actually write the solution of the PD as an expectation. So to summarize, we just concluded, combining the two slides before, that the expectation is a solution of the quadratic minimization problem, and using the Feynman-Katz representation, which tells us that for a linear parabolic PDE, we can actually write the solution of the PDE as the expectation. We just found that the solution of the PDE, denoted here by BTX, can actually be written as, or characterized as, the solution of this quadratic minimization problem. So since we have now found an optimization problem for which the solution of a PDE is a solution of our optimization problem, we take this optimization problem, we use neural networks to try to learn to solve this optimization problem, and then the neural network which does the job will approximately be the PDE. But however, if you remember what I was saying at the very beginning of the talk, is that for linear PDEs, actually we have already efficient methods to solve high-dimensional PDEs. So here the Feynman-Katz representation works for linear PDEs, but our goal is to develop neural network-based algorithms for non-linear PDEs, because sophisticated models which are more realistic turns to correspond to non-linear PDEs. And for linear PDEs, we have already efficient methods. So more precisely, we are interested in not linear PDEs, but semi-linear PDEs. What do we mean by semi-linear PDEs? Is, you see the blue term is exactly the same as we have seen before, but now we have an additional term here, f, which might be a nonlinear function on the solution and on the gradient. Okay, and you might also want to add a nonlinearity in the Hessian, but for simplicity, we just assume nonlinearity in V and in the gradient, so that the PD becomes nonlinear. More precisely, semi-linear, but particularly it's not a linear PD anymore. So, so the goal is, these are typically financial prices of financial derivatives can actually be expressed as solution of semi-linear parabolic PDEs of this following type, for of course, depending on the model you choose, corresponding sigma, mu, and f's. So these are the type of nonlinear PDEs we would like to solve. And since they are nonlinear, we can neither apply the classical Monte Carlo methods, nor can we directly apply the Feynman-Katz representation, because as we've just seen before, Feynman-Katz representation only works for linear PDEs, and this is a nonlinear PDEs. So it's not a new idea, completely a new idea to try to use neural networks for nonlinear PDEs. I just named some to name but a few people who actually worked on developing machine learning based algorithms to solve nonlinear PDEs, to name but a few. And the main idea there is actually to use what is referred as a nonlinear Feynman-Katz representation using BSDs to write the solution of the PD as a squared minimization problem. However, and the results were extremely promising, extremely strong, in the sense that before, with the classical methods, they were actually able to solve PDEs of dimension 7, 8. Now with those machine learning based algorithms, they were able to solve PDEs of dimension 200, 300, which is already a very huge improvement regarding the dimension. The key point why we were, and this was our key point when we started to build our algorithm, which is different from the existing ones, is that using this, what is referred nonlinear Feynman-Katz representation, this is actually an implicit representation of the solution of the PDE, whereas the classical Feynman-Katz representation, if I go back to the slides quickly, you see that the solution of the PDE is, in the linear case, is really explicit in the sense like on the left-hand side, you have the solution of the PDE, and on the right-hand side, this does not depend on the solution of the PDE at all. So it's really an explicit expression. So what we would like to do is we would like to somehow reduce the case back to the linear, to a linear PDE or to several linear PDEs to be able to use the classical Feynman-Katz representation, because an explicit expression would hopefully allow to be more efficient and hopefully to be able to solve PDEs even in higher dimension than 200 or 300. So the key idea of our approach is we have our nonlinear PDEs as written here above. With here, this corresponds to the linear part, and the red part corresponds to the linear part, nonlinear part. And what we would like to do is we would like to treat the linear part and the nonlinear part separately, what is referred as splitting method, and use this kind of trick to somehow use then the classical Feynman-Katz representation rather an implicit representation, what is somehow referred as the nonlinear Feynman-Katz representation. So now let me introduce to you the algorithm. It's going to be a little bit technical, but don't worry, for those who are not familiar with stochastic calculus, I'll try to re-emphasize on the main ideas, and particularly later on I will go back to the numerical results. So for those who it's going to be the next 2 or 3 slides, a little bit technical, don't worry about it. You can catch up later again. So let me first introduce to you the main idea, okay? The main idea of our algorithm is the following. So we have our time grid, 0 to big T. Big T, think of it at the time where your contract ends, like the example which I gave at the very beginning was 1 year. And what we're going to do is we're going to discretize the time into n points, so n grid points, but we do not discretize in space, but only in time, okay? So we divide our time interval from 0 to t in n parts, or n+1 parts. And what we're going to do is we know at the maturity at big time t, let's say in 1 year, we know exactly the value of the contract. That's exactly the value which the bank has to pay to the owner of the contract. As we said before in the example at the very beginning, it was exactly the difference. You were above 120. So if the value of the stock was 130, you would gain $10 from the bank. If the value of the stock was 130 in a year, then you would get $20. If it was below 120, you will not get anything. So you know exactly the value what the bank has to pay to you at the maturity big T. So this is well known. And now what we're going to do is we're going to go backwards in time. From each time interval tn+1, we try to evaluate the value of the financial derivative at the time point tn. So at the end on the left-hand side of your time interval. And what we're going to do is we're going to approximate the PD in the following way, that the linear part here, we don't touch it all. So you see this is exactly the same as for the PD under consideration. However, the nonlinear part we discretize in time. So instead of what you would have is the integral between t and tn+1, and with respect to the time, you just take the time at the right-hand point, tn+1, and you multiply it with the time difference. So here you see the nonlinear part has been discretized in time, whereas the linear part has not been discretized at all. And this is what we refer as the splitting part, because we treat the linear part and nonlinear part differently, in the sense that the nonlinear part is discretized in time, whereas the linear part, we don't touch it all. So you see this big V, and this big VTN is somehow can be seen as an approximation of our solution of the PDE at time Tn. And why is it a clever approximation? Because now you see that the nonlinear part now here does not depend on time anymore. It does not depend on t anymore due to the discretization. So in other words, as a consequence, you can actually show that this big V, which is an approximation of your PDE, the little v, now solves the actual linear PDE, but on the time interval between Tn and Tn+1, okay? With the boundary condition Tn+1. So if you start at the very right end, you start at big T. let's say big T is Tn plus 1, you now, by this approximation of big V, you found an approximation which solved the linear PDE without the nonlinear part F, and with the boundary condition, exactly the same boundary condition as your boundary condition at time big T, which is exactly the boundary condition phi. So what do we get from this is, now we're back to business, because now we have found an approximation which solves a linear PDE, and the linear PDE is exactly of the type from which we can actually now use our classical Feynman-Katz representation. So how does the Feynman-Katz representation this type looks like? We look at the corresponding SCE, which is exactly what we learned from the Feynman-Katz representation, and using what is referred in the stochastic calculus as Ito's formula, and using the definition of the PDE, we can actually show that the solution of this approximation, big VTN, applied to this STXTN. Don't forget, we go backwards in time from Tn plus 1 to Tn, or let's say from, if Tn plus 1 is big T, from T to Tn. Then this can be actually written using Ito's formula as a conditional expectation, okay, for each time T. And if we let T goes to Tn plus 1, and using the formula for VTXT, if you remember what was VTXT, was exactly the following. And if I let T goes to Tn plus 1, this integral vanishes. So this disappears. So the only thing which is left is exactly this term here. So if we plug this in, we get actually that VTN can be written as the conditional expectation of the future time Tn plus 1, Vtn plus 1, xtn plus 1, plus this time, plus this part here. Conditional information at time xtn. So in particular, what you see is that if you go backwards in time, at time big T, you know the value V big T, because this is the boundary condition phi. And now you can recursively go backwards in the sense like, if you know the value Vtn plus 1, xtn plus 1, you can now represent your time at Vtn. You can express the value of Vtn, xtn as conditional expectation, which is nice because we have just learned before that the conditional expectation is actually a solution of a quadratic minimization problem. So in particular, what we have just learned is that Vtn is actually a solution of this quadratic minimization property, by the property which I showed you at the beginning regarding the minimization property of an expectation or conditional expectation. So what is the idea of our algorithm is, instead of trying to solve the whole PD at the same time, what we're interested is at the value V0x, because that's the value of your PD at time 0 at the current time. So instead of trying to solve the PD at once, which is a nonlinear PD, the idea is to first define a time grid, and on each and divide this whole time interval 0 to t in n plus 1 time intervals, going backwards. So from t to tn plus 1, tn plus 1 to tn, tn to tn minus 1, tn minus 1 to tn minus 2, and so on till you reach 0. And for each time interval, you're going to use a neural network which should solve this minimization problem which we have here, which depends on the position Vtn plus 1 on the previous position, which was already trained before. Because again, you start from the very right side at the maturity. At the maturity, you don't need to train anything because you know the value of your stock, which is the boundary condition of your PD, which is exactly the boundary of the PD. So it's exactly phi of x. And then you backwards, you try to use a neural network to solve this optimization problem. This gives you then the value at time Vtn. You have trained your neural network to solve this, and then you go from the interval Tn to Tn plus 1, you go to the next one, you go to the time interval Tn minus 1 to Tn. The value at Tn you have just trained before, and you're going to use this value to train a new neural network, and you do this recursively n times till you reach time 0, which gives you a neural network which approximately gives you the value V0x. So how does the algorithm looks like? So first of all, the boundary condition The boundary condition is known, so there's nothing to train at the maturity. So, and then what you're going to do recursively from n plus 1 to n, you learn the optimal parameters of your neural networks using, for example, a classical software, like let's say TensorFlow. So how you do this, you, from a computational point of view, you first simulate the paths of those corresponding SDEs, which you need for the Feynman-Katz representation. And then what you're going to do is recursively, you're going to try to train all those neural networks for time tn plus 1, then time tn, then time tn minus 1, then tn minus 2, and so on. So you're going to train totally n plus 1 neural networks. And the training involves, as we know from machine learning, you're going to apply the gradient descent method, which here I just defined the plain vanilla gradient descent method. You can, of course, use more sophisticated methods to actually solve the corresponding optimization problem, which looks complicated, but is exactly the one which we just have derived before. And so to summarize what is the idea is, instead of trying to solve the whole nonlinear PD at once, you divide the time interval from 0 to t in n or n plus 1 smaller time intervals. And at each time interval, you can approximate, let's say from tn to tn plus 1, you can approximate the nonlinear PD by a corresponding linear one. You solve this approximated PD, which is linear one, using Feynman-Katz. At time tn, you use this solution to go back to use this as the boundary condition for the next time interval tn minus 1 till tn. You use again an approximated PD with the new corresponding boundary condition VTN, which is just your trained neural network at time n. You get a new neural network for time tn minus 1. You do this backwards till you reach time 0. And once you have reached that, you find the neural network. You have the value of the PD under consideration at time 0, which is exactly the price of your financial derivative at time 0. Okay. So this was the technical part. For those who it was a little bit too technical, I apologize for that. But I really hope that you get the main idea that the splitting method, by looking at, by treating the nonlinear part differently from the linear part, you end up, instead of one PD, with n approximated linear PDs on the corresponding smaller time intervals. You solve them recursively, which leads you to the solution of the PD, of the approximate solution of the PD at time 0, which is exactly the price right now of your financial derivative, which is expressed as the boundary condition of the PD under consideration. So this is our splitting method. Now, of course, you may ask, how well does it work compared to classical method, but also in comparison with other machine learning based methods, which were using different kind of arguments, as mentioned, for example, the nonlinear Feynman-Katz representation. So let me show you one numerical example to give you a concrete example of a PD. Let me introduce to you to the following example, which is the nonlinear Black-Scholes model with default risk. So let me introduce to you this model. So this model is not a model which we developed. This is a well-known model in credit risk and in financial derivative pricing. But we use this one to demonstrate that the algorithm works very well. So let's start with the Black-Scholes model with interest rate R bigger to 0. This is the classical, let's say, the first model which was used to price financial derivative and which led to the authors to get a Nobel Prize. And as said at the beginning of the talk, this is a linear PD. So for this, you have also for high dimensions, very efficient methods to solve it. But now, in addition, we add, compared to the classical Black-Scholes model, we add that there is actually default risk for the claim. What do we mean by default risk? If default occurs, the owner of the contract of the financial derivative only gets the fraction delta, which delta is a fixed value between 0 and 1 of the current value of the actual contract. So here there is default risk, and you may ask yourself, how can you model this? So one way to model this is, how can you model default? So you can model default by just the first time of a Poisson, of the first jump of a Poisson process, which has intensity Q. generalized Poisson process in the sense that the intensity Q depends on the position of the PD, depends on the value of the financial derivative, where so the intensity, and we assume, and I will tell in a second why this is reasonable, that is actually a decreasing function of the current value of your financial derivative. Why does it make sense? Because the less value of your financial derivative is, the less value means also that there's a higher risk of default. So that's why the higher the intensity, the higher is the chance that that the Poisson process jumps. So in other words, the higher is the chance that default occurs. So actually you want that the intensity is a non-decreasing function of the current value, namely the higher the value of the financial derivative, the less risk you should actually have that default occurs, or equivalently, the lower the value of the financial derivative, the higher is actually the risk that default occurs. To specify a concrete model, we choose a very simple function for Q, namely just a piecewise linear function with 3 regions. So this looks a little complicated, but it's actually very simple, and I can explain this very easy in words. So you have 3 regions. First regions is for the value of your financial derivative between minus infinity, or if you assume that it has to be at least 0, from 0 till a fixed value UH, you have a certain constant intensity lambda gamma H, where gamma H is to assume bigger than gamma L. And then for a value from mu L on, where mu L is a higher value than mu H, you assume that the intensity is gamma L, where gamma L is smaller than gamma H. And between mu H and mu L, you just linearly interpolate. So in other words, but if the value of the financial derivative is, let's say, from 0 to mu H, you have an intensity gamma H. And then you linearly interpolate from the value mu H to mu L linearly till you reach mu L. And from mu L on, you have intensity gamma L constantly. So this is a very simple decreasing function, nonlinear function. It is actually piecewise linear because there's just one king, constant, then linear interpolation between mu H and mu L, and then again constant. But it's a nonlinear function for the intensity. And what you can show, and I refer to the paper who developed this model, so Bender et al., you can actually solve that now if you have a Black-Scholes model with default risk, where the default is modeled by the first time the Poisson process jumps, which has intensity Q as specified here. You can actually show that then the corresponding PD is of the following type. And you see, so this is the same as we had before, linear in time. So you have in the gradient, you have linear in V, linear in the Hessian, but you see here, it depends on the solution Q. You apply to Q, you apply the solution of V, and you remember Q is not linear, it is piecewise linear, but it is not a linear function. So in other words, this PD here, now, because we have default risk, becomes a nonlinear PD. Originally, the Black-Scholes PD is a linear PD, but if we, as soon as we just impose this little assumption of having default risk, it's not a very sophisticated model, but just adding default risk, our PD already turns from a linear PD to a nonlinear PD, for which classical methods are not able to solve them in high dimension. High dimensions mean the dimension of the PDE is high, and which means that the corresponding boundary condition phi, which is the contract of your, which is the financial derivative, depends on the assets. So what we want to show now, and I will demonstrate to you now, is we applied our algorithm to exactly this kind of PDE for corresponding boundary condition or to a corresponding financial derivative. And I will show you our numerical results, which hopefully will convince you that the algorithm can deal with very high dimensional PDEs. So first, let me, for those who are coming from computer science or data science averse people, affine people, let me explain to you the neural networks which we are actually using. So what we use is we have a d-dimensional input layer, which is exactly just the value of the PD, which is exactly the value of the prices of the underlying stocks at time 0. Because we have d stocks, so that we just have to give in the exact value of those stock price at time 0. And then we use a very simple structure of the neural networks. We use 2 hidden layers of dimension d plus 10, and the output layer is 1 dimension, is exactly the price of the corresponding financial derivative. And what we do is we run this algorithm 10 times and we take just the average, okay? And we train this using TensorFlow on the following computer. I don't want to go too much into details, but what I would like to emphasize is that, first of all, the architecture is very simple. Second of all, we have trained this on a more or less normal, usual computer, which every one of us can have at home. So in particular, we didn't want to use any kind of supercomputer or any kind of fancy architecture of our neural networks. Not that people can actually claim that our algorithm works well just because we use some kind of very fancy architecture of the neural network, or we have used an extremely strong computer, and it's actually not the algorithm which does the job, but the computer power. No, we purposely computed it, simple architecture, more or less simple computer which every one of us can have at home, such that we can really convince that even with a computer which every one of us can have at home, with a simple architecture, really this kind of not very deep neural network, we can actually get good results. So let me now present to you the results which we have. So as a boundary condition, we just take the minimum of xi. So it's just, we're going to look at, so the contract will just gives you the minimum value of all those d assets. So this is what you're going to get. So let's say if your contract depends on d financial derivative, the bank has to pay you the minimum of the value of all those d involved stocks at the maturity, let's say after 1 year. Okay, and you may ask, how much does it cost me under this default model if the bank after 1 year has to give me exactly the value of the minimum of all those d involved stocks which were under consideration? And we were asking ourselves, what's the value of this financial derivative at time 0, given that I know the value, of course, of the d stocks at the current time 0, at the current time now. So what we get here is this table where you see, depending on dimension, the results. In particular, what I would like to emphasize is here the dimensions. So we are able to actually solve this nonlinear PD in dimensions 10,000. So you see that this our algorithm actually gives an additional improvement in the dimensions than before, than the algorithms before, because as I said before, like the first algorithms which used neural networks were able to solve approximately nonlinear PDs dimension 200 and 300. And now our approach, by using neural networks, but by not losing the implicit representation, but by using this kind of splitting arguments, by treating the linear part differently from the nonlinear part, which allows us to reduce the case to the classical Feynman-Katz representation, allows us actually to go even higher and allows us to treat high dimensional PDs up to dimension 10,000. So in the paper, we actually have also different PDs also coming from physics, Allen-Kahn equation, Hamilton-Jacobi-Bellman equation. So feel free to have a look at those. But I think the key idea, the key reason why our algorithm works better is really that by instead of looking at one PD and trying to solve this like on the whole time interval, and instead you divide it into n time intervals, and for each n time interval you approximate the nonlinear PD by a linear one, and you're solving this recursively. This is very efficient and allows you to go even higher in the dimensions. And the results, thankfully, allow us to resolve up to 10,000 dimensions. So which means we can price financial derivatives in sophisticated models, which involves up to 10,000 financial derivatives. In particular, we can, for example, deal now with financial derivatives, which involves the whole S&P 500, depending on 500 assets. So you see the algorithm works well, but now you may ask, why neural network? Why did we actually start with neural network? Of course, as I said, we have the universal approximation property, and we have seen that in other fields, such that like speech recognition or classification, computer vision, neural networks like really worked very well. But you might ask yourself, okay, what was actually the reason? Is there a fundamental mathematical reason why actually you had also hope that it does the job well for solving PDEs up to the universal approximation property. And there is a deep reason for it from a mathematical point of view or from a complexity theory point of view, which tells you that actually neural networks overcome the curse of dimensionality. And what do we mean by neural network can actually overcome the curse of dimensionality? Let me present you one theorem. There are several theorems of right now. I mean, this is a very ongoing research in the last 3-4 years, but let me present you one which is suitable to do the talk, which tells you the following: like if D is the dimension and you take any probability measure and you consider such a PD, okay, which is a nonlinear PD, but I would like to emphasize that here the nonlinearity is only in the solution of the PD, not in the gradient. Still, it's a nonlinear PD, a semi-linear PD, but it does not involve nonlinearity in the gradient, but it covers, for example, the example of the Black-Scholes with default, because if you remember there, we just had the nonlinearity in V and not in the gradient. Let me go back to show it to you. The PD here, the nonlinearity was only here, so it only involved V and not the gradient. So for this kind of results, actually, you can show that neural network overcome the curse of dimensionality really from a theoretical point of view, which means like for any given accuracy epsilon, you can find a neural network with the numbers of parameters only growing polynomially in D and epsilon, such that in the L2 norm, the error is actually smaller than the accuracy epsilon. So this really shows you that neural network can actually overcome the curse of dimensionality, because given the accuracy epsilon, it only grows polynomially in D and epsilon, the amount of parameters which you need to have in your neural networks, which is an indication that actually, okay, the neural network can really do the job well for high dimensional problems. Particularly, so high dimension means for very high D. As I already mentioned, this is a very ongoing research. So far it is understood for nonlinearity in V, and of course one would like to generalize it for also nonlinearity in the gradient or in the Hessian. So these are not clear results so far, but people are working on it, and hopefully one can get results soon also in that direction. So open questions, as already mentioned. So first of all, can we also actually really prove that neural network overcome the curse of dimensionality for more general nonlinear PDs, HGB equation of fully nonlinear PDs? Because if you have optimization problem from stochastic control theory, typically your nonlinearity will not only be at the solution B, but also in the gradient, which is not covered by the theorem just presented before. And also, if you, for example, those who are coming from finance, if you want to involve model uncertainty, for example, volatility uncertainty, the corresponding PD even becomes nonlinear, fully nonlinear, not only semi-linear, but fully nonlinear, because you have also nonlinearity in the second derivative. So, of course, the question is, can we actually also prove that neural network can overcome the curse of dimensionality? So this is one thing. Second thing of all, and this is a mysterious and an open question, probably one of the most important open questions in machine learning theory, not only for our problem here, but machine learning theory or neural network involved algorithms in general, is why do neural networks actually do a good job? So if you remember, what we have seen is neural networks possess the universal approximation property, which means that every continuous function can be approximated by a neural network. But this very abstract result from function analysis doesn't tell you how to choose the neural network, what is the geometry, what are the right parameters of your neural networks. And in practice, what you do is you train your neural network by solving a corresponding optimization problem. And training is done today automatically using software like PyTorch or TensorFlow. But, and this is the big but from an optimization point of view, those optimization problems are typically non-convex, okay? So for example, in the example of what we had, our corresponding function which we were optimizing is really not, it's highly non-convex. Highly is of course not a mathematical term, but it's far away of being convex, roughly speaking. Still, you apply, when you apply TensorFlow to train your neural network, you try to to solve this optimization problem, which is non-convex, so for which you don't even know if a unique minimizer exists, if a minimizer exists, if your neural network will actually find the global minimum if it exists, or a local minimum, or just a stationary point. Yet people apply neural network, and yet we have seen in applied science that neural networks do the good job, as I said, in computer vision, speech recognition, classification, despite the fact that the training, when applied to neural networks, actually corresponds to solving an optimization problem, which is non-convex. So this is really an open problem in the theory of neural networks, why they actually do a good job. And this is really one of the open questions in that field. A lot of people are working on it. For example, in our case, we have a result why stochastic gradient descent algorithms converge in the strong sense. But of course, under some convexity assumptions, which unfortunately neural net in practice do not involve. There are different research going into that direction. We, for example, here in our group right now with a postdoc, with Ying, we are trying to understand it for the non-convex case in some special situations. So this is really a high topic right now in research in theoretical machine learning, and hopefully at some point we will be able to fully understand why machine learning, why neural networks actually can learn this, not only from the universal approximation, but why actually when applying the training, when applying TensorFlow or PyTorch, actually neural network does the good job. So I think I spoke now about an hour, so let me summarize what we have learned today. So I introduced first the motivation of why we would like to solve high-dimensional linear PDs, why it's necessary in finance. And I introduced to you our concrete deep learning-based algorithm to solve semi-linear parabolic PDs. The main idea was the splitting map method, namely to distinguish the linear part from the nonlinear part, which allows you to, instead of solving one PD, we discretize the time and into n time interval, and for each time interval we approximate the nonlinear PD by a corresponding linear PD, for which we use n neural networks. So we train recursively n neural networks from the maturity t, for which the boundary condition is known, till backwards, till reach time 0, the current time, to be able to get the solution of the PD at time 0, which corresponds to the price of the financial derivative at time 0. And the key idea to be able to use this, we use Feynman-Katz representation. And further, we discussed further challenges, which hopefully in the future will be able to give you further insight about this theory. So in that sense, for those who are interested, the paper can be found on my webpage. Is right now in the this submitted and hopefully very soon accepted. It's right now under minor revision, but the paper is available in archive. And if you have further interest in my research or about this paper, you can also find it on my homepage. So in that sense, thank you very much for your attention. I'm very happy to discuss with you further if you have any questions.
Thank you, Prof. Ariel, for such an insightful talk. Now, I would like to invite our co-host Shantanu from the School of Electrical and Electronic Engineering to host the Q&A session.
Thank you, Shubham. And thank you, Professor Ariel, for making math sound a little more interesting to us. Now, attendees who would like to ask Professor some questions, you can use the raise hand feature at the bottom of your Zoom screen. Or you can send in your questions in the Q&A section, and then I'll read the questions out to Professor, and then he'll answer them. So before we move on to the questions in the meeting, we had a few questions sent to us by the participants during the registration. Let's take a look at those questions first. The first question is from SK Ong, who would like you to explain a little on the possibility of having an inverse neural network to predict what factors would result in a target price.
Okay, so maybe I go to answer this. Let me look here. As I said before, you see this PD typically in finance. So first of all, if you want to price a financial derivative, you first need to make some model assumptions. And as I said, typical model assumption involves some stochastic differential equation, which then leads to that the price of the financial derivative can be written as a solution of a semi-linear parabolic PD, which is of the following type. So you see phi is the boundary condition, which is the financial derivative, but you see you have functions sigma, you have mu and f, which are functions which you need to specify, which depends on your model, which you want to choose. So now the question to one of the colleagues was, can we actually invert it? Can we somehow train the parameters? And this, of course, can be done because now, if, for example, for each, if you have to specify f, mu, and sigma, you get the corresponding solution v of the PD, which depends now on sigma, mu, and f. And if you have prices already given, you know that the price should be the solution of the PD. So what you could do, for example, is just, roughly speaking, take the quadratic error between the solution of the PD with respect to the parameters f, mu, and sigma, and the real price, take the square, and now try to optimize over f, mu, and sigma in the sense like you want to find corresponding functions which satisfy this. That said, of course, I mean, if you need to optimize over functions, this is an infinite dimensional optimization problem, which is in practice difficult to do, but you can reduce this by saying, okay, instead that the function f is any kind of continuous function, or mu or sigma, you do this with, let's say, in a parameterized version, that you have a function structure, which you have to specify some parameters, and you train over these parameters. But yes, this can be done under the condition, of course, that you know the price, and then it's really just classical supervised learning with the quadratic error.
Great. I hope that was good enough for SK Ong. A next question is by Kenzie, and the question is a little more general. And the question is, what did you do to obtain your knowledge in this field?
I mean, I think that's in typical mathematics. It's reading, talking to colleagues. I think, I mean, if you wanna learn a new topic, and first of all, I mean, in your education, you were specialized in a certain field. So everyone comes with a certain deep knowledge. So my personal knowledge, I'm coming from Stochastic Calculus, Stochastic Optimal Control Theory. So my background is really financial math on the probabilistic side. But then, as you've seen, people then had the idea to somehow use Stochastic Calculus and probability theory to tackle problems in machine learning. So if you have this already knowledge, you can learn new theories, let's say this whole new theory about machine learning. But if you want to get into this field, the best thing you can do is read papers from the leading professors in that field, try to attend workshops, or now today, also now with all those webinars, it's much easier because you can just attend mini workshops, read books. Try, for example, to see if at your university you have a professor who is doing research in that direction, see if there is a lecture which he's offering, or if he or she doesn't have such a lecture, maybe he or she can offer you some literature or books. But I mean, the best thing you can do is really try to read papers regarding this field, and also try to find mini course or webinars regarding the topic. But once you reach a certain level, I think the best way in mathematics or in general research is at some point you need to start research trying to find a project, because if you just read without trying to solve a problem, you practically speaking, you will forget a lot what you read in very short time. So the best thing is to try to get first a deep knowledge, but once you reach a certain point, try to get a good project, either by which popped up after reading a lot of papers, or by discussions with colleagues, or maybe with the corresponding professors, because then once you have a concrete problem in mind, you have also motivation to read other papers, because you have, for example, some phenomenon which you try to understand, which you don't know how to solve. And with this problem in mind, you're going to read and try to find literature to solve this problem. And with this, you also increase your knowledge.
Thank you, Professor. Now we will move on to the questions given to us by the audience. The first question, and it has 2 thumbs up. So the first question is by Brandon Chu, and the question is, if the problem is solved recursively, would there be a buildup of error for each time step of some sort?
Yes, I mean, of course there is. It's a good point. So, of course, as you say, there's a trade-off. There's a trade-off, of course, because as you say, on the one hand, you would like to have as many time grid points as possible, because because I mean, on each time interval, you do, of course, an approximation of your PD, because you have this kind of approximation where you discretize in time the nonlinear part. So of course, the smaller the time interval, the less error you have. But of course, first of all, for each time interval, you need to train a new neural network. So this will also, first of all, be costly from a computation point of view, because instead here we have n time points, but imagine you have 2n time points, so you need to train 2n neural networks, one for each time interval. And second of all, as your colleague was saying, of course, each approximation is not exact, so there comes errors. So in that sense, yes, there's a trade-off, and this is an engineering part of point to find the right balance of how to choose those time intervals in such a way that the error is small and also the computations don't get too heavy, in the sense that we're still able to efficiently solve high-dimensional PD.
Thank you, Prof. Our next question is similar to the question asked during registration, but perhaps I might try to zero it down to a little specific. So the question is from Zhang Yipeng, and the question is, he says, "Hi, Professor. It looks absolutely alien to me as I am not in this field. It's very intriguing, and may I know your recommendations for some good resources to get started in this area? Thank you in advance." And you talked about this in the second question asked, but perhaps could you maybe give some recommendations for someone in, say, the field of electronics?
So I mean, you see here there were. So here what I use is some kind. This kind of algorithms combines two or three things. First of all, if you want to get to know the idea, what's the connection between why does the price of a financial derivative corresponds to a solution of a PDE? This is something which you can read in every classical book in financial math. This is something, if you take a course, for example, in financial mathematics, either here at the math department or at the business school, you will learn the connection of, if you assume a corresponding model which is Markovian driven by a stochastic differential equation, then the price of the financial derivative can be written as a solution of the PDE. So if that is something which is not understood, I recommend to look any kind of classical book in financial math. Second thing what we used was exactly this relation between PDEs, which you want to solve, and stochastics, like the stochastic differential equation, that we can write the PD as an expectation, which is the Feynman-Katz representation, which is one of the core results in stochastic calculus. So, of course, this is somehow involves deeper understanding in stochastic calculus theory, but I recommend in any classical book in stochastic calculus, you will find these results because it's really one of the core results. But for this, it involves the knowledge in first of all, measure theoretical probability theory and then stochastic calculus. So this is probably from a technical point of view, the most difficult to learn because it involves like advanced probability theory and stochastic calculus. But for those who are interested, I highly recommend to do so. And then the machine learning part actually is the smallest part in that sense. Is once you realize that you can combine this, then it's actually more the idea to combining this rather than the difficulty from a machine learning point of view. Because as you have said, once you have identified that you can combine stochastic calculus with machine learning, you have identified your optimization problem, and then you just apply classical programming to try to solve this. I mean, here I presented just gradient descent method for simplicity. We used a little bit a more sophisticated one, Adam optimizer, but actually you can take whatever you want. So in that sense, for those who have a good knowledge in how machine learning works, how you can train your networks, this is the easiest part. The key idea is really how you can combine stochastic calculus and the knowledge from mathematical finance in such a way that you can formulate the price of a financial derivative in such a form that you can apply classical machine learning methods. How to train then the neural network efficiently? This is then more an engineering point of view. Of course, you need to find the right hyperparameters and so on, but it's then more on the engineering part. So to really understand this, why this algorithm works well, I think this from a theoretical point of view, try to understand financial math, why prices of financial derivatives can be written as solutions of PDEs. And second of all, stochastic calculus, which tells you why solutions of PDEs can be written as an expectation, namely this Feynman-Katz representation.
Thank you, Prof. That was those are some good suggestions. The next question is by Jevin Siatriadi. And the question is, hi, Prof. Thank you for the great talk. My question is on partitioning the time interval. Does the partitioning affect the output significantly? In particular, what will the output be if the time is partitioned equally?
So I'm not sure if I understand your question correctly. So you ask, how does the result affect if we choose different time intervals? So I mean, what we did at the end, of course, is we tried to find the optimal ones. I mean, what we did is we used equal partition. Of course, you may of course try to optimize this to find optimal time grid. What we did is very simple, just T over N to really have equidistant. A priori, you don't have to. So actually, you can really try to even optimize our algorithm to find optimal time grids. But that, again, was not our goal. Our goal was really to say, our method is really, instead of trying to solve the PD directly, you divide it into n time intervals, and for each time interval, you approximate the nonlinear PD by a PD1, a linear PD, for which you apply Feynman cuts, and then we can use a neural network for this time interval to train it. But how to find the optimal time parameters, that the optimal time grid to optimize the solution, in a sense, like to make it even more efficient in high dimensions or to reduce the error, is actually we didn't even analyze, because this was really not our goal, and we leave that for example, this could be an interesting FYP project or Eureka project to try to optimize this. But this was really not our goal, because in the same reason that we haven't chosen a very fancy architecture here, is really wanted to, and we have chosen a simple computer, is really to show that even with the most simplest method, like equal time grid, a simple architecture of the neural network, no fancy neural network, on a regular computer, which you and I can have at home, the algorithm works well. Rather than people could claim that, yeah, you took you 1 year to optimize some kind of crazy parameters and time grid to work. So this was not the goal, and it's really the modeled really equally time grids. Yeah.
Thank you, Prof. Next question is by Tushar Vaidya. The question is, what type of neural network architecture is typically used?
So what do you mean by typical? So what we use is this one. I think this should answer the question. So you see, it's a very simple one. One input, two hidden, one output. You see also the dimension. Okay, D and one dimension, of course, are clear. The D dimension correspond to the prices of each stock at the current time. So we have D stocks. So these are the prices at time 0. One, the output layer is exactly the price of your financial derivatives. But you see, we just use two hidden layers, and the dimensions are just D plus 10. So again, the reason was to use very simple architecture, such that people can actually not claim that we were trying to crazily optimize the geometry of the neural network, but rather by using a very simple architecture to show that actually the algorithm works well. Feel free to try to analyze how it can actually do better by changing the geometry or the depth of the neural network.
Thank you, Prof. Our next question is by Jinlong Guo. And the question is, hi, Prof. Why was Python software chosen to run the algorithm? Does it have advantages over, say, MATLAB or R or C?
I mean, TensorFlow particularly is exactly useful because it allows you to efficiently do the optimization, which involves the training of neural network. Why TensorFlow, no PyTorch? There's no particular reason in that sense. I mean, people who are using neural networks to train, they either use today TensorFlow or PyTorch, but in that sense, there's no particular reason from a scientific point of view, from an engineering point of view. I mean, you have backward propagation. I mean, the software is exactly built to train neural networks, so we use just the classical most used software. But there's no particular reason you could have used PyTorch. But again, the idea is that we reuse simple architecture, the most used software on a simple computer, to re-emphasize to the people that we haven't tried to go into crazy architecture, crazy software, crazy superpower of a computer, but rather a simple architecture on the standard software which you and I would use at home, on this classical computer which you and I have available, and yet the algorithm does a good job. So TensorFlow is probably, if I would ask you one software to program neural networks, probably most of you would have chosen TensorFlow or PyTorch, So we have chosen TensorFlow, but there was no particular reason for that.
Thank you, Prof. Our next question is by Tushar Vaidya. The question is, why solve high-dimensional PDEs when hedging strategies for multi-options portfolio might also work, or are those the same thing?
So first of all, I mean, portfolio theory is not the same as pricing. So pricing is exactly, you have a contract. As I said, for example, you have a contract which, let's say in the one-dimensional case, you have one stock, which has right now value 100. And the bank offers you a contract and you look in 1 year the value of this asset, of the stock. And if it's above 120, you get the difference. So if it's 130, you're going to get $10. If it's 140, you're going to get $20. But if it's below 120, you don't get any money from the bank. And now the bank is offering this contract, and you may ask, what is the fair price for this kind of contract? So this is a financial derivative, and you ask how to price this. So this is a pricing problem for a given financial derivative. So contract, as explained here depends on one asset. Of course, in practice, you have not only one asset involved, but several ones. So the dimension D corresponds to the amount of assets involved in this contract. Whereas portfolio optimization is, of course, the question is you have a certain amount of money and you can invest in certain stock. And the question is now, how much money should I put in each stock? Should I put 50% of my money in stock 1 and 50% in my stock 2, or should I put everything into one stock? So this is portfolio optimization, which is a different topic. Of course, one can try to also use machine learning for portfolio optimization, but it's not what I would want to talk about this today.
We have 3 more questions. The first one is by Jin Longguo. Hi, Prof. What do you think will be the long-term industrial value of research in this direction, which is using machine learning to solve stochastic PDEs? And will it make some bank operations more efficient?
We hope so. I mean, that's the goal. At the end of the day, this kind of machine learning technology, or now also quantum technology, is really the goal to make stuff more efficiently. Because I mean, we're living in the 21st century, which is the century of data. So I mean, right now, I think one of the most prestigious values are actually data, and typically data are extremely high dimensional. So you need to find methods to actually deal with those high dimensional problems efficiently. And machine learning, for example, neural networks, but of course other machineries how to deal with it, turns out to be very efficient. So on the one hand, you would like to build machineries involve modern numerical methods, like, for example, machine learning, like neural networks as I presented here, to price high-dimensional financial derivatives, or to minimize risk, or to do portfolio optimization. Because I mean, typically, I mean, like stuff which are involved are not depending on one stock, but maybe on the whole index. So you have several indexes involved, and so this naturally makes sense that one would like to build such algorithms which work well. And also, as a mathematician, as an applied mathematician, you not only want to develop an algorithm which works well, but our goal as a mathematician is also to understand why they work well, because it is somehow dangerous to just develop algorithms which are kind of a black box, in a sense. They work well from some problems, but if you don't really understand why they do the job well, you have always this kind of risk that maybe in some kind of extreme situation, from a financial point of view, let's say if there's a market crash, there might be that your algorithms don't work, and that's exactly typically the time where you want that your algorithms work efficiently and correct. So us as a mathematician, we don't stop by just saying we want to build an algorithm which works well, but we want to also understand from a mathematical point of view why they work well, because if we understand what they work, we also understand their risk, and we can try to optimize the algorithms in the sense that we can minimize the risk. So in that sense, our research is really both sides. On the one hand, to develop those algorithms which can deal, me as a financial mathematician, problems, or which improve pricing, minimizing risk, optimize portfolios in high dimensions, but also from a mathematical point of view to understand why those algorithms work well. Because of course, from a theoretical point, it's interesting, but also from an application point of view, it is important to understand these, because only then we can really move from a black box to really an algorithm which we understand, and we can also control the risk when applying them.
Thank you. Our next question is by Sofa Singh. And the question is, can your method be used to calculate the Greeks, example, theta, or the time decay rate of the option price?
So that's a good question. I mean, you could, but it's more involved. So here I was always only talking about the solution of the PD, whereas the Greeks involves derivatives with respect of the solution. So there are methods to deal with it. I mean, you have representations which involves Nanyang calculus. I don't want to go too much into that here, but you can, using Nanyang calculus, you can actually formulate this also to learn Greeks. But I mean, this algorithm was really focusing on the value of the price, and you can also actually learn the hedging strategy. But Greeks, yes, can be used, but then it involves also, in addition to the Feynman-Katz representation, it involves also what is referred as the Nanyang calculus. But yes, a priori you can do this, but for those who are interested in that, I also recommend to look at the theory of Nanyang calculus.
Thank you. Our next question is by Arun Vijay, and the question is, hi, Prof, does the use of an ANN in financial risk credit necessitate the same approach used for nonlinear PDEs?
Can you maybe repeat the question?
Yeah, sure. The question is, does the use of an ANN in financial risk credit necessitate the same approach used for nonlinear PDEs?
I'm not sure if I understood the question well, but I guess if I'm not sure if I understood the question well, but I mean, in general, you have typically problems which are high dimension, for example, credit risk, so you have risk of default and so on. So these are typically problems which involve several parties, not only like one parameter. So this becomes typically a high dimensional problem for which classical algorithms are not efficient. So as soon as you have a problem which is high dimensional for which classical methods somehow are not efficient, it's naturally today with the modern numerical methods like neural networks to try to build a neural network-based algorithm which can solve this. If you can apply one-to-one this machinery, it's of course, I mean, one needs to analyze this. I mean, you see why we were able to use neural networks here was in the sense like we know from financial mathematics under some model assumption, the price can be written as the solution of the PD. We write the PD as an expectation using Feynman-Katz, and we learn a neural network to solve this, roughly speaking. Now, of course, depending on what the person wants to analyze, one needs, of course, to think of how can one connect the actual problem which one wants to solve with, how can one connect this with the machinery of neural networks which one can use. So here the key trick was really to this transformation of pricing, PD, expectation, quadratic minimization problem. You can write an optimization problem, which then allowed to use neural networks. For this particular problem, okay, this is a case-by-case basis, but this is part of research to really come up with a good idea how one can formulate the problem in such a way that it's suitable that one can apply neural networks.
Thank you. Next question is a little, it's a long question, so I'll try to make sure you get it properly. It's by Chikun Chiang. Question is, I wonder if people have tried training the artificial neural network in, say, 7 to 8 dimensions with a small number of samples and compare the results with the results from classical method like finite element to see if the artificial neural network generalizes well at those X that are far away from the samples. I'm asking because in high dimensional settings, due to the curse of dimensionality, the samples used for training the ANN will become very sparse.
So we didn't do this for low dimension. I know some other people did that. Yes, exactly for that reason. What you can also do is, I mean, you know that our method, as you have seen, is very general, for very general structure of PD. But what you can do, for example, if you look at the very particular structure of PD for which you know the solution explicitly. So in general, from PD theory, you know that if you write down a PD in general, you cannot solve it explicitly. There are very, very few ones which you can rewrite the solution explicitly. But for those ones, for example, what you can do is actually you can compare the analytic solution with for which you actually would not need to train a neural network, but you can compare this with what the neural network does to compare exactly if it does well. And for those which you have no analytic solution, yes, you could do this. I agree. We haven't done this for this method, but other people did this. But also other methods actually kept it more on the lower dimensional case. So there are actually some algorithms involving neural networks, but their results are also kept in the low dimensional case. So we could have done this. We haven't done this in our paper, but we have used also examples for which there are different methods which allow to calculate those high dimensional PDEs, and we compared the errors. In that sense, we can really show that our algorithm performed well for those PDEs under consideration.
And our final comment is by Tushar Vaidya, and it relates to a question that was asked before. He says, my question was on deep hedging a portfolio of options versus high dimensional PDEs. And just for your reference, the question that he means is, why solve high dimensional PDEs when hedging strategies for multi-optional options portfolio might also work, or are those the same thing? So the comment that he has put up is that this question was about deep hedging a portfolio of options versus high dimensional PDEs.
Okay, so I mean, if you want, okay, so the point is, if you want to, so the one thing is about depending how do you define, let's say, the price of a PE. So what you can do, for example, is of course you can say you want to do, let's say, quadratic minimization. So if you think of hedging, you want to, for example, you have a certain financial derivative, and your goal is to hedge it directly. So what you do is, from a financial mathematical point of view, you look at the quadratic error and you try to really minimize the error by exactly, you look at the optimal hedging strategy which minimizes quadratic error. You can do this, and for this you actually don't need PDEs, I agree, but this is a different method how you want to do it. So again, since typical financial markets are not complete, so there's not a unique price. So it's the question of how you model and how you define the price of a financial derivative. So if you define it in such a way that you want the quadratic minimization, then you can do this exactly with the hedging approach. And I can recommend you the paper by Lukas Gorno, Hans Bühler, Josef Teichmann, and I think there was a fourth author. I'm really sorry if I don't remember the fourth author, which is called Deep Hedging, which exactly brought this idea up. So you don't need any PDEs because they reuse the quadratic minimization problem, which they train directly the neural network to find the optimal hedging strategy. On the other hand, if you use this kind of assumption that your pricing model is coming from an SD, we know exactly the price is exactly the solution of the PDE. So once we have the exact solution of that, we know the solution is solution of the PDE, and actually the hedging strategy can be also characterized as its derivative, then it naturally makes sense that once we agree on this model assumption, that we want to solve the PDE. But again, it's a question how you formulate the price. If you want to do it by quadratic minimization, you really try to use this deep hedging approach, how it was done by Hans Bühler, Josef Teichmann, Lukas Gorno, and co. If you want to do it really via like pricing, in the sense like you have an underlying model for which you know that the price is the solution of PDE, then it makes sense that you want to solve the PDE because you know exactly the price is exactly the solution of this PDE. The hedging strategy can be also expressed via derivative with respect to the solution. So since you know this from theory, you want to ask, okay, can I find an algorithm which efficiently solves this PDE approximately? Because you know, in theory, the solution of the PDE is exactly the price. So this is somehow the question of how you want to start with how to define the price of a financial derivative. But for the question, if you want to see for this quadratic hedging approach, I refer to again Hans Bühler, Lukas Gorno, Josef Teichmann, and the paper is called Deep Hedging. It should be easy to find online on Google.
Thank you so much, Professor Ariel, for patiently answering all those questions.
Thank you all for coming, and thank you again for the opportunity to speak here. Again, if you read the paper is publicly available, and if you want to see more about my research, feel free to go on my homepage, where also the paper is available.
Thank you. So we would like to thank the audience for coming. Now, please scan the QR code, which will be shared on screen in a few minutes. We will upload that now and provide your valuable feedback. Also, you can indicate the need for endorsement of the attendance. So can we have the QR code, please, Chris? QR code is up on your screen, and please scan it and fill it up. Thank you. That's all from my side.
Thank you so much.
And yeah, thank you.
Have a nice day and thanks for coming.